Good morning, everyone, and welcome to today's webinar. Let me start with a big thanks for attending the webinar today on behalf of Future Electronics and onsemi. This webinar is going to be recorded and it will be made available for all the people registered to the event. My name is Riccardo Collura. I am the Global Power Segment Manager at Future Electronics. The title of the webinar today is Mastering Power Factor Correction from Fundamentals to Vienna Rectifiers, and the webinar is co-presented by Future Electronics and onsemi. So let's start by introducing you, the presenter. Christophe Basso is a business development manager at Future Electronics based in Toulouse, France, covering EMEA. Previously at onsemi, he led an application team dedicated to developing AC/DC and DC/DC switching controllers. He has originated numerous integrated circuits, among which the NCP 120X series has set new standards for low standby power converters. Christophe has published 10 books on power electronics, and the last one being released in September 2024. He holds 25 patents on power conversion, and he has taught many seminars in IEEE sponsored conferences like APEC in the US. Christophe has over 25 years of power supply industry experience. Prior to joining Future Electronics in 2021, Christophe was a technical fellow at onsemi and an application engineer for Motorola Semiconductor in Toulouse. He holds a Diplôme Universitaire de Technologie from Montpellier University, France, and MCEE from the Institut National Polytechnique of Toulouse, France. He is an IEEE senior member. Didier has received his engineering degree in the École Nationale Supérieure d'Électronique at the Radio-Électricité de Bordeaux in France in 1992, and his PhD degree in power electronics from the University of Bordeaux in 1997. In 1996, he joined AEG Power Solutions, formerly Alcatel Converters, as a research engineer for DC-DC and AC-DC converters design in a range of 1 watt to 1 kilowatt, mainly for telecom equipment. He managed the research activities from 2000 to 2014. Didier published more than 10 papers on power electronics, and he holds 1 patent. From 2011 to 2013, he worked 18 months on a 15 kilowatt solar inverter, DC-AC module, for a 150 kilowatt cabinet in Dallas, Texas. His main interests during this period were switching mode power supply, converter stability and modeling, and high power factor rectifiers. He joined Fairchild Semiconductor in August 2014 as a field application engineer supporting south of France, Spain, and Portugal. In 2016, onsemi acquired Fairchild. In 2018, he moved to a new role inside onsemi. Didier is currently a business market engineer for Europe, focusing on power device and silicon carbide. Now let's have a look at the agenda for today. First, Christophe will talk about PFC simulation for different topologies of single and three-phase applications. After that, Didier will present onsemi Elite Power Simulator with some practical examples. At the end, we will have a Q&A session, and during the session, I will be posting some links that can be useful for you. In order to have your privacy guarantee, please use the question box for your questions, and we will try to answer to all the questions today. However, if we run out of time, all the unanswered questions will be addressed privately afterwards. Christophe, the stage is yours.
Merci, Riccardo, for the kind introduction. So, hello, everyone. My name is Christophe Basso. I work for Future Electronics, as Riccardo mentioned. I joined in 2021. And today's 30-minute seminar is about active power factor correction simulation, and it will take us around electrical, let's say, these electrical circuits designed for single and three-phase networks. So this is the agenda, and during this session, we will review some of the main components that we can find in active power factor correction circuit. The apparent power absorbed by a load supply from a sinusoidal source is made of real and imaginary parts that we designate as active and reactive power. The active or average power, P, is expressed, as you know, in watts, while the reactive power, Q, is expressed in VARs, V or RS, volt amperes reactive. And when mathematically combined, they lead to the apparent power S, which is expressed in volt amperes or VAs. The ratio of average power to apparent power determines what we call the power factor of the load that we abbreviate PF. So when a resistive load is connected to the mains, apparent and active powers are identical, and then you have a power factor which is unity. Now, if you connect a 70-watt AC-DC adapter whose front-end rectifier consists of a diode bridge and a capacitor, the average power keeps nearly the same, assuming they are absorbing the same amount of power, but the RMS current is much higher than in the resistive case, bringing a large apparent power. In this case, the PF is barely equal to 0.6. A power factor less than unity induces a larger circulating RMS current for a given active power. That's what we saw with the previous example. So imagine you have an AC outlet whose maximum RMS current is limited to 15 amps. You could only connect 3 250-watt workstations in the given example. Now, if you insert what we call a pre-converter or power factor correction stage for each workstation, they will bring their PF close to unity. The nominal input current now drops to 2.3 amps for each computer, and you can connect up to 6 workstations now. And the burden on the power cord is also reduced, and you can use a smaller wire gauge for the assembly. After a few lines of algebra, the power factor can be expressed by the product of two parameters that you can see on the slide. It's Kd, the distortion factor, and K phi, the displacement angle. So if we assume a sinusoidal source, when the current is also sinusoidal but phase shifted by an angle phi, the power factor is equal to cos phi. Okay, it's only valid for sinusoidal waveforms. But when the current is distorted, with the fundamentals still in phase with a sinusoidal input source, the PF is linked to the distortion factor as shown in the graph. An active power factor corrector circuit will shape the input current to make it sinusoidal and emulate resistive load. Now, if we look at the instantaneous power absorbed from the mains, it is the product of the input current and the input voltage. The result is modeled by a squared sine wave whose average value is the power transformed by the load into physical work. That's the blue graph you can see on the right side. It is 150 watts in this example. And if we plan to develop an active power factor corrector to emulate resistive behavior, then our PFC circuit will need to also store and release energy as illustrated. You can see, if I start my pointer now, sometimes there is an excess of power, sometimes there is a shortage of power, and while the average power is still 150 watts. So doing this thing, let's say having more power or less power at some point of time, it will result in a voltage ripple appearing on the output, and its frequency is twice the input source, like 100 hertz, or if you are talking about a 50 hertz environment. For stability reason, you will set the control loop crossover frequency of the active PFC sufficiently low to exclude the ripple components from the regulation path. Otherwise, of course, the loop will react on its own ripple and deteriorates regulation. Now, if we look at a balanced three-phase system, the total power absorbed from the grid is the sum of the individual power supplied by phases A, B, and C. If you plot these individual powers separately, as you can see here, you classically obtain the squared sine wave, but when you sum them, you unveil a flat line, which is here, which is the total instantaneous power spread among the resistive load. As such, the need for storing and releasing energy as in a single-phase application emulating resistive load is inexistent in a three-phase PFC. This example shows the low-frequency output ripple between a single-phase and a three-phase PFC, delivering the same amount of power, which is 3 kilowatts. From, let's say, the input line, in that case, is a 120-volt input line. The single-phase output shows a grid ripple with a peak-to-peak value here of 40 volts. You can see here on the red line, the peak-to-peak is quite high. Of course, if you would like to reduce this ripple, you would need to, let's say, increase the output capacitor. But that would not be a problem with the three-phase PFC, delivering the same power. The DC bus here, as you can see, it's the same simulation on three phases, with 3 phases. The DC bus is flat for an identical output capacitor value. To obtain these waveforms, I'm very often resorting to what we call average models, and they're very useful for determining the small signal response of a switching circuit. In this example, I use them to simulate the low frequency component present on the output voltage and undergone by the output capacitor. In the single-phase application on the left side, this component alone heavily contributes to the RMS current. So we're talking about the RMS current circulating in this capacitor. And this RMS current will be made of the low-frequency component, the high-frequency pulses coming from the PFC, but also the high-frequency pulses absorbed from the load in the end. On the contrary, with the three-phase application that you can see on the right side, the low-frequency component is inexistent, and you can see here. So the current flowing into the capacitor, at least for the low-frequency ripple, is extremely low. And what you will have as the big RMS current flowing into this capacitor, as in the let's say single-phase application, will be the high-frequency pulses coming from the PFC and the high-frequency pulses delivered to the downstream converter. However, there will be no AC components, no low-frequency AC component. Let's have a look now at some of the various electrical architectures. A traditional active power factor correction circuit uses a boost converter. That's most of let's say the most common topology you can find, but you have also other topologies that can be found, such as the buck converter or even the CEPIC. The boost, however, largely dominates the market, particularly in the consumer electronics world. In the boost converter, the inductor current is the input current. Therefore, imposing a sinusoidal envelope to the inductor current makes the average input current also sinusoidal. This technique lends itself very well to implementing PFCs in various conduction modes for power level, let's say ranging from 100 watts to several kilowatts in the case of multi-phase structures. As expected, the output voltage is affected by 100 or 120 hertz ripple, whose amplitude depends on power and the bulk capacitor. Now, if you look here, this is a familiar, let's say, full bridge diode rectifiers that you can see. And in the classical single-phase boost PFC, the front-end diodes, this bridge here, affect the efficiency by dissipating power and cost. If you look at a very classical, let's say, calculation here, around 2% of the budget in this 300-watt example. The diode bridge disappears in the totem pole PFC or TP PFC, which processes the input voltage according to its polarity. You have one active high-frequency average in the left side. This is called the fast leg. These are these transistors. And a classical low-frequency diode average in the right side. Of course, here you can have synchronous rectification across these diodes. In these structures, Q1 and Q2, they alternate between the role of either a main switcher or the rectifier. It is therefore important to decode the line polarity and drive the active parts accordingly. The TP PFC structure is known since the 90s actually, but has only become popular recently, more or less recently, with the introduction of wide bandgap transistors, which feature zero or low switching losses when recovering from the conduction in the third quadrant. The output voltage of a boost power factor correction stage is selected based on the maximum peak input voltage. So let's say if you have a 265 volt RMS single phase input, usually a 380 or 400 volt DC output is usually adopted. But some applications which operate down to 85 volts can dynamically set different levels for improving efficiency, as minimizing the conversion ratio also reduces losses, of course. In a three-phase application, the rectified voltage would peak close to 600 volts. So the DC bus is usually regulated at 750, 800 volts. This high level imposes severe breakdown constraints on the semiconductors and the decoupling capacitors, as you can imagine. So by splitting these 800 volts into two separate 400 volt rails, as you can see here, so this one would be the middle point, and you go to plus 400 and minus 400, or 0, 400, and 800. So this is what a three-level converter will offer. It is an interesting way to select lower breakdown voltage components by supplying the downstream converters from 400 volt DC source. This is a classical example here on the left side. It truly simplifies the stacking of power converters, which will now operate with a lower voltage stress than if directly powered from a single DC rail. The floating outputs can be combined in series or parallel to deliver more power. These interleave single-phase converters, as you can see, this is single phase, this one, but still three output level, never had a lot of success considering the floating connection of the input source naturally leading to an unfavorable EMI signature. This is another structure that you can see on the left side here. It's also a 3-level, and this is a single-phase architecture. So we have 2 switches which are connected back-to-back here, and a low-frequency rectifier with 2 capacitors here. One of the switches is always turned on in the half on the input line cycle, while the other performs the high-frequency switching action. For instance, S4 is on during the positive cycle, and S3 switches, while S3 is on during the negative cycle, and S4 switches. The off-time voltage across the inductor is half of the output voltage in this application, which means that in theory, for a given wanted input current ripple, the inductance can be half of that in a 2-level PFC. And if you are familiar with it, it resembles the single-phase version of a Vienna rectifier. But please note that the output voltage must be twice the input peak value here, imposing an 800-volt DC rail here in this single-phase application. As any power converter operated in closed loop, a PFC needs to be compensated. And I use a simulator like Simplis, which is what we call a piecewise linear simulator, and it lends itself very well for running an AC simulation when the circuit has reached steady state. The periodic operating point trigger is synchronized with the input line, so you can see the line is still present in this simulation. There is no DC bias, as you would need to do that with a classical SPICE engine. And it lets the engine plot the compensated loop gain response. The transient waveforms of this T-type PFC confirm the correct operation. Here you can see the operating point that has been calculated, and then the compensated loop gain here shows a crossover of something like 4 Hertz with a 60 degrees phase margin. But here you would obviously need this is a simplified version, but you would obviously need high side drivers for the 2 T switches here. But the cool thing to keep in mind here is that even with a switching circuit, a software like Simplis can extract the AC small signal response. Even here, if you have an AC stimulus powering the PFC stage. The 6-pack structure is a front-end converter commonly found in high-power 3-phase systems. It is naturally bidirectional and can be scaled to several tens of kilowatt or more via interleaved approach, for instance. The control strategy of the transistors ranges from a single 3-loop arrangement to a more complicated space vector modulation scheme. The Vienna rectifier on the right side, this is this converter here, it was patented in 1993 by Professor Kolar for Axis semiconductors, which is now little used. It is a 3-level converter, as we've seen before, which obviously lets you stack power converters supplied from 400-volt DC rails. The stress on the semiconductors in this Vienna is reduced, and you can use 650-volt rated components, even if you have a 0 to 800-volt bus voltage. And finally, the control of the back-to-back switches is simplified compared to that of the switch 6-pack approach. An additional control loop is usually necessary to keep the output balance here. So the voltage here should be, the spread should be equal between the 2 capacitors over here. So there is usually an extra loop on the control of these switches, which is going to add a small duty ratio, let's say value, to compensate for the change of voltage or the unbalanced operation between the 2 capacitors. Let's have a look now at how power factor correction is realized in single-phase networks. So boost PFC can operate in different modes, and this is true not only for boost PFC, but also for, let's say, a variety of switching converters. And the mode can change depending on power and line levels. What we call borderline conduction mode, which is abbreviated BCM, you can find it as well under the CRM, critical conduction mode, or boundary conduction mode, BCM. It implies a variable switching frequency to keep the inductive current always discontinuous at the border between DCM and CCM. In absence of dead time, it means here you can see there is almost no dead time. The power switch is turned back on when the inductor current is equal to 0. Then the average current is exactly half of the peak. So if you take the peak here and divide by 2, well, you exactly have the average current, which is over here. So it means if you impose a sinusoidal envelope in BCM to the inductor, the average inductor current, which is also the input current, that's why it's interesting to adopt a boost converter, is also sinusoidal. So you can see here the envelope here has been sinusoidal. So we impose a sinusoidal envelope on the peak current, and the average current naturally is also sinusoidal. In practice, there is a small dead time that we add here. We add a small dead time to make sure that the drain voltage swings to a minimum value. We call it valley switching, and it reduces the turn-on losses. In CCM, on the contrary, the inductor is always greater than 0, and except near the 0 volts region where VCM can be observed. This operating mode requires an inductance value which is naturally larger than in VCM, but core losses and RMS currents are reduced in this mode. The diode being brutally blocked by the transistor turning back on, you need a low TRR type or SiC diode, which can be selected for the best efficiency and reliability. Finally, recent PFC controllers, they transition between these operating modes to improve THD and light load efficiency. This is the boost converter that you can see operated in a self-relaxing quasi-resonant operation. There's no clock in this circuit. A dedicated winding across the power inductor helps detecting valley of voltages and the core reset, if you want, when the inductor is fully demagnetized, and it signals the controller to restart the switching cycle when this happens. As is with any quasi-resonant operation, the switching frequency runs away when the input voltage approaches zeros, and it induces current distortion as the on-time becomes minimum in this area. And efficiency can suffer in light load operations. There are plenty of techniques and IP to slightly increase the on-time around the zero crossing and improve distortion. And please note that there is no voltage sensing in this configuration. In current mode control, it's a bit different, but the principle remains the same. The inductor peak current is sensed and leads to the same constant on-time operation as with voltage mode control. And the peak inductor current this time is monitored via sense resistance in the MOSFET source, and it follows the rectified input voltage scaled via the error amplifier and the multiplier. So there you go. You have the multiplier which is there. This is an image of the input voltage, which is going to give you the rectified, the Vrect over here. And then the error voltage, by biasing one of the input of the multiplier, is going to scale up and down the voltage applied at the modulator. So demag winding is still needed here across the power inductor, as the circuit also operates in quasi-resonant mode. In average current mode control, the inductor current is continuous and monitored through a dedicated high bandwidth current loop. There is an extra loop which is added, which is here. The set point is given by the multiplier output, which imposes a current in the ROCP resistance, which is this resistance here. The set point, again, is made sinusoidal through the sense of the input voltage multiplied by the error amplifier. This is a two-loop system needing power compensation. So a small signal analysis shows the power stage gain dependency on the input voltage, and some circuit offers compensation to keep an almost constant crossover frequency regardless of the input level. And you can run the simulation here of a TP-PFC, again, through Simplis. All these platforms are available for simulation for free. You can download them, and I think Ricardo is going to share the link in the chat station. You can import these Simplis platforms and run the simulation with your program, or even for some of them with the demo version. So the simulation on this CCM TP-PFC, implementing variability of technique, is fast and lasts at least 1 minute for generating the transient and AC plots. And the crossover at low line is set as a few hertz, as you can see in this example. And you can look at the THD and many variables here using this TP-PFC. So we are now going to see solutions for three-phase networks. So needless to underline that it's a very vast territory with many difficult trails, and we will only explore a few here. It is possible to use the classical fixed frequency boost structures adapted to three-phase applications. So remember here, we need to control the current and the distortion in 3 phases now. So compared to what we had before, we have 3 phases. In this mode, the current distortion is very high, you can see. So there is, I'm duplicating what was done before. There is, let's say, a diode bridge over here, 1 inductor and 1 transistor. And when I do that, the current distortion is very high at 35%. You can see the waveforms. The current input current is not very nice. The adopted modulation strategy is the variable of time we have seen, but there are natural conduction holes in the front-end diodes which prevent from having a sinusoidal input current. These are the holes you can see here during the time during which some of the diodes are blocked. And despite its implementation, it does not really offer suitable if you want a low THD, besides its regulation function, of course. So it means you could use that guy over here as a very rough DC voltage rectifier and regulator, but not for having a good THD. We can also try one single switch and 3 inductors. So again, in between, one single switch, but we have 3 inductors that are now placed in series with input sources. And this is the PFC delivering 3 kilowatts. The RMS current in the transistor it's 3.8 for 400 volt AC phase to phase level, and the peak currents are about 13 amps. The circuit includes a specific circuit to limit the maximum switching frequency, but also so-called what we call a watchdog to restart the system in case the DMAX status is missing. In this simulation, the THD is a bit better, but it's somewhere around 10 to 12%, which is much lower than the first single switch boost converter, but still fairly high. If we look at the waveform in the balanced three-phase network, the input waveforms are delayed by 120 degrees, implying a certain combination of polarities at a given time. So we can distinguish different sectors, what we call sectors, to identify the phase voltages. The sectors are numbered from 1 to 6, and you can see that in sector 1, which is here, phase A is positive, and actuating switch SA would let you increase the current and classically boost the voltage via D2. However, as phases B and C are negative, as you can see they are negative here, well, in that case, the body diode of the transistor would permanently conduct, and actuating the switches beside providing sync rec would be useless, okay? Because you could not impress a sinusoidal, let's say, wave shape. In sector 4, now we have 2 positive phases, and we can drive switches SB and SC, as we can see here, for impressing the desired sinusoidal shape. Theory states that if you can control 2 phases, the current in the third is automatically controlled, considering the sum of the instantaneous currents being equal to 0. With this simple architecture, this would only be possible in selected sectors, confining this structure to regulation purposes again. The 6-switch configuration, also known as 6-pack or B6, is a popular arrangement used in high-power 3-phase power factor correction modules. Several techniques exist to drive the power switches at moderate frequency for IGBTs, let's say down to a few, let's say kilohertz, 10 kilohertz perhaps, and end up to 30, 50 kilohertz for SiC transistors. The structure can be interleaved to spread the power dissipation budget on more semiconductors and, of course, reduce the stress per capita. We are first going to look at the 6-step modulation technique, which consists of turning off one leg while the remaining 2 are active. If you look back to the previous foil, because there is at some point the body diodes that are conductive and you cannot use that leg. Let's see what a 6-step modulation implies. If you look at the sinusoidal waveforms in the upper right corner, you see, again, that in some sectors, one phase is positive while 2 are negative. This is the same situation that we described a few slides before. In sector 1, the body diode of SAP will permanently conduct, and you cannot control the current of phase A in this period of time. The same situation arises in sector 4, where the body diode of switch SAN will conduct, and you cannot control the current in this phase at that time either. As a result, the logic block will disable leg A in sector 1 and 4, leg B in sectors 3 and 6, leg C in sector 2 and 5, while concentrating the modulation effort on the phases that are not disabled. In this foil, you can see a 3-phase PFC configured in a 6-pack architecture with individual phase current shaping. The error voltage scales the amount of high-frequency current imposed to each inductor via dedicated multiplier. So it's a classical single-phase approach here, but replicated 3 times. I could have used average models to extract the control-to-output transfer function of this power stage, but I used Simplis, which delivered the AC response in a few minutes. The type 2 OTA, which is somewhere here, is compensating for a 100 Hertz crossover frequency, because I can push crossover in three-phase system because I don't have the issue of ripple anymore. So you can see here, this is the decoding for the sectors, which is going to route the PWM signals here for actuating the switches here, depending on the position on the sectors. In this example, the power is first set to 12.5 kilowatts and suddenly increased to 25 kilowatts. The nominal deviation is only 12 volts, which corresponds to roughly 1.5% of the nominal output voltage. The crossover is set to 100%, to 100 Hertz, sorry, and this value is made possible in absence of course, low frequency ripple as in single phase PFC. And THD is not too bad, it's 3.9% in this application, but you can see that the loop is really stable. So DQ0 transformation is a term that you will see quite often if you start digging into three-phase PFC, but it's a complicated matter. But I can try to, let's say in a nutshell, to explain the approach. So in single-phase PFC, we have one single AC source, and as we've seen, it is relatively easy to shape the input current sinusoidally while ensuring a zero phase shift with the voltage. In a three-phase network, we have three AC sources, phase shifted by 120 degrees. And we want to ensure output voltage regulation while absorbing a sinusoidal current and keeping the reactive power to the lowest on each individual phase. One possibility is to transform the three variable input voltage into two DC components representative of the active power. This is D, and the reactive power, which is Q. D will be imposed for a given P out and actuated or regulated by the loop, while D is kept to zero. And it's kept to zero, of course, if you want to emulate a resistance. If you would like to emulate a capacitive load or capacitive components or an inductive component, of course, D can be controlled for this purpose. And the way to go for a three AC variable frame to a two DC component system is to use the DQ0 transform made of the Clark and Park transformations. So you can see here from the sinusoidal input, you go through this mathematical transform and you have two DC components. Then once the two DC components are regulated and changed depending on the power or the type of, let's say, impedance you want to offer to the network, you go through the inverse transform to recreate a sinusoidal set point that will be sent to the modulator. Processing the DQ0 signals requires the access to input current, but also to the instantaneous angle computed via a phase lock loop. Since we want the reactive power to be zeroed, well, we set IQ to 0 while ID is adjusted for regulating the voltage bus. The stability studies is extremely complicated for three-phase PFC, and the seminar whose link is given in the slide offers an excellent resource for this subject. So here we've compensated the crossover frequency of the voltage loop to 20-30 Hertz, while the DQ0 loops are going to cross over around 2 kilohertz. And I'm using the, let's say, the sinusoidal PWM modulation here with a 30 kilohertz carrier. It's interesting to build average models of the three-phase PFC for determining the small signal model transfer function. I've used here the average switch model developed by Vachiev-Vorkarian in 1996, and it's, let's say, operating in continuous conduction mode. The switch duty ratios are replaced by the small signal gains of the pulse width modulator, and the simulation time is a few seconds at least to obtain the transient response. And if I do things well, I can then open the loop, the individual loop, and inject an AC stimulus for obtaining the AC response. These are average models. Always look that the DC bias points you observed before considering the AC results are correct and meaningful, because otherwise you could have, let's say, very bad DC operating points and still having AC response that would be correct, of course. So each loop is compensating using a type 2 circuit, and you can see this is what I have obtained here with Symmetrix Spice. I'll show how to do the same with LT Spice. And you can see here I've got 20 Hertz crossover frequency, 2 kilohertz for the D and Q loops, and I can run the simulation now and see the results. The new simulation that I'm going to run is a cycle by cycle model that I'm going to use to check the good relationship between what is the average model, what are the average model results, and what are the cycle-by-cycle model. Of course, this simulation is much longer than before because there are, let's say, cycle-by-cycle transition, even if I don't use perfect switch. And you can see the THD is about 4.5%. And then the good thing is I can check here the relationship or the difference between the average model and the cycle-by-cycle model. You can see average, there is no ripple, and cycle-by-cycle, there is some ripple. They are exactly identical, making me believe that the average model is validated by the transient analysis. This is a 6-pack circuit, this time using 6 transistors, so it's going to take longer for simulating. I'll always recommend that you start small with let's say, a classical perfect switches, and when the overall architecture of the PFC is delivering the adequate results, then you can update the circuits with either drivers, these are simplified version, or the true model of your switches. Because when you start having switches like with the real model, it's going to take time before simulation is over. I can reproduce again a Vienna rectifier using LT-SPICE, and you can see here the Vienna rectifier using perfect switches. And I can also, because it's very important using whether you deal with this circuit or this circuit, to make sure that the loop here are properly compensated. So in LT-SPICE, you can see this is the AC analysis of the Vienna rectifier using average models. Some of the models are not used because it depends on which diode here is going to conduct and which one is blocked. So I can simplify here to only have 3 models. And it's important here to look at the operating points to make sure that the model has properly converged towards a solution before considering the AC result. But otherwise, the principle remains the same as we've seen before. You extract the AC small signal response for each of the DQ0 loops, the same for the voltage loop, and then you can think about a compensation strategy. Everything is automated here on the right side. Just enter the magnitude and phase extracted from the body plots, and then the macro will compensate the compensation components across these elements. Of course, all these examples in LT-SPICE are available from my website, and I believe Ricardo has already pasted some of the links in the chat window. And now, if you run the simulation, whether this is cycle by cycle or this is, let's say, an average model, you can have access to the sinusoidal input currents and run THD analysis. Check if you would like to, let's say, implement here. You could implement some balancing between the 2 capacitors here. There is a 4th loop in that case. Usually it's made with a low gain regulator that would help you compensate here the unbalanced situation between the 2 capacitors. I also have examples of these 2 guys. Okay, so we've seen that we were reaching the conclusion now. So we've seen that PFC is a hot topic for several decades, and you can use analog implementation for, let's say, single phase application. You start having digital control, but it's more in the compensation side, where it's good to have on the fly, let's say, compensation changes for keeping a constant crossover frequency regardless of the input voltage. And because compensation is internal, the time constants at play for having a low crossover frequency are compatible with hardwired digital processing. The TP-PFC is gaining traction, obviously, especially in high-density chargers, and because it's owing to semiconductors like GaN and SiC who have very low recovery losses. 3-phase PFCs is a very complex matter, and if you would like to study the subject, I recommend you start studying rotating machine first, because many terms and mathematical expressions come from that field. And most of the PFC projects I've seen, they deal with digital control. But nevertheless, simulations helps a lot here if you like to assess losses, of course, but also understand how these DQ losses are operating and how to compensate them. So I'm done for my side, and thank you very much. And I'm gonna, let's say, hand over to Didier in a second.
Thank you, Christophe. So, Christophe, you were introducing how to calculate losses. So let's move to how to calculate losses when you have such PFC. So We can calculate losses using SPICE model, and in onsemi we have a unique SPICE modeling technique that we call physical and scalable modeling. This was made for having very accurate results, and we did that by adding to the SPICE default model equations that are linked to the structure. So many devices in SPICE are created in the 80s, and now with the new technology, we have included things like trench gate or vertical device, various doping region, and so on. So all those parameters that are physical, the doping value, the structure type are included, and also the mechanical or the dimension, like the thickness of the oxide, the length of the polygate, the depth of the P-well, and so on. All those dimensions are part of the model. Also the layout of the die and also the package. So in the end, we attach all those parameters with new equation to an electrical schematic that come from SPICE. This is an example, for example, for the capacitor. We have several capacitors stacked together depending on the doping and the size of that region. And this is why here you see those equations that we add to the capacitor. And you can see that those capacitors use the doping as a parameter to represent the capacitor value. Then when you use those models, we can compare the datasheet value or the measurement value that are the dots here compared to the simulation. This is the straight line. You can see I can capture the fact that with temperature, the capability of the device to conduct current decrease with temperature. We can see the same thing on the gain. For example, here on the linear curve, I can see that the gain saturates with the temperature, meaning that I can conduct less and less current. I can see on the load scale here, the same curve. And here I can see that I have an accuracy of 4 decades with that model. I can capture the fact that the body diode voltage decreases with temperature. This is what you can see here. But also I can generate curves that are not available in the datasheet. For example, the RDS1 versus temperature, the VTH versus temperature. So all the curve you need that is not included in the datasheet can be simulated. You can also simulate the capacitor. You see the straight line again is the simulation, and the dots are the measurement. And you can see how accurate we can fit the output capacitor value. And in this way, if we fit the capacitor value and all the value, we can predict in a very accurate manner the losses. Those models are made to be dynamic also. Here is an example of a double pulse tester. I can see things during the turn on, the fact that when I have high capacitor value for low voltage on the drain, my charging will take time. And you can see that here on the drain voltage, as we have a average configuration, one has a low voltage, one has a high voltage, it starts slowly to decrease and then go faster because I changed the COSS value. So I changed the speed of the drain voltage. I can predict the overcurrent during turn on that is linked to the reverse recovery, but also to the COSS and some parasitic component present in the circuit. I can predict also the voltage dip inside the gate voltage on the pink waveform here. I can use that also for turn off to predict the over voltage at turn off and also the speed of the current going down. We have introduced also online a new tool to evaluate losses, and I will go down in this tool that is a 2-in-1 tool. In fact, the tool is composed with a self-service PLECS model generator that will generate the PLECS model, and this is based on a SPICE engine to generate the PLECS model. And the SPICE model we are using are the physical and scalable model we've seen just before that are very accurate and allows us to predict the losses. The second part of the tool is called the Elite Power Simulator. It's just a PLECS engine working online that will generate the losses. And you can see that you can pass the model you have generated to the topology simulator, the Elite Power Simulator. And in this way, if you have a model corresponding to your environment, you will get very accurate losses. So why we decide to make a model generator for PLECS and not giving you a default model? I can call the default model or the nominal model or the shining diamond model, because this model is made in a much possible perfect environment. We obtain those models by using physical and scalable model in SPICE to predict the losses, but we also include in the model you will generate in the model generator compared to the default model or nominal model, we will include the surrounding and the parasitic component that will affect the losses. For example, the parasitic capacitor of the inductor will limit the bandwidth of the switching inductor, and so at some point the inductor can turn to a capacitor, generating high losses inside the switches. This is captured by the model generator. We can generate a large amount of data that is difficult to obtain by measurement to have accurate interpolation and extrapolation, and also depending on the range you will define, we will see we can remove extrapolation error. We have included a new double pulse or losses tester that we call full switching tester that is able to predict the losses in hard and soft switching. And we will see that it's very useful when you need synchronous rectification. So how the self-service PLECS model generator works? In fact, you have the switching loop represented up to the bus bar with some inductor to connect the device, and then you have also the decoupling capacitor, local decoupling capacitor, and your switching inductor that we call the load of the switching loop. And you can also describe the damping network you can use above to damp the DVDT, for example, on the switch, and describe also your driving circuit. All those parameters will be captured and will represent your board environment to give you your model that will represent the real losses that you will observe, taking into account the full environment of your structure. On top of that, you will need to enter the range where the model is valid. So you can here enlarge the range to have the model operate always in interpolation, and in this way remove extrapolation errors that are more critical. So at the end, you obtain this model with all the dots are the points included in the model. You can see we can capture really the non-linearity and all the variation. For soft switching, we don't give you any default model because soft switching depends on your design. It will depend on the resonant inductor you have choose, on the DIDT range that will appear in your inductor, and also in the dead time between the two switches. This dead time impact if you were in full soft switching or if you will operate in partial soft switching or in hard switching, depending if you have enough resonant energy to fully switch or not with the time you have set. So for that, you need to include extra parameters like the delay between the switch, the resonant inductor, and this DIDT. Most of the time, you can take -10 +10 as a current. It's not so non-linear, this parameter. Or if you are in low voltage and high current, you can use 100 and -100. So at the end, you get this model with a much more point, as you can see here. We can capture really the transition between hard switching, partial soft switching, and full soft switching with negative ion. And you can see here also, you have various shapes here. So the model is complete, and you can see the transition between all switching conditions. So at the end, when you look at the on/off, you see that we can provide the first quadrant that corresponds to the main switch in hard switching configuration, but also the third quadrant that corresponds to synchronous rectification operation, because synchronous rectifier operate in the third quadrant in the direction of the body diode. And in this case, you see it's the same quadrant as the soft switching. So soft switching models are useful for synchronous rectification. The difference between the two is the resonant inductor value. In soft switching, you will make this inductor large enough to have enough resonant energy. In synchronous rectification, you want to decrease this inductor as much as possible to have a fast transient and operate in synchronous rectification. So now let's move to the topology simulator, the Elite Power Simulator. In fact, we have a lot of topology available for automotive application or industrial application. For AC/DC, you can find the totem pole PFC, the T-type Vienna converter, as Christophe explained, the 6-pack. And also for low voltage, we have dedicated topology for low voltage, like active clamp flyback or active clamp forward with low voltage output. And in this way, you can use also low voltage device like our T10 medium and low voltage silicon MOSFET for synchronous rectification. We have included all silicon carbide product, silicon carbide MOSFET and JFET discrete and module. We have included also the FinStop 7 IGBT in PIM module or IPM or smart module. So at the end, the Elite Power Simulator group a very large range of topology. We are the only one to provide low voltage topology. So in total, you have more than 60 topology possible for DC-DC, AC-DC, and DC-AC that can cover domain like DC fast charger, UPS, energy storage, OBC, or traction. We provide you corner simulation as we know the physical parameters, we know their variation, and so we can provide you extreme model, not only the nominal or the average model. We can provide you some extreme model to see how our process affects the losses of your system. You can use custom PLECS model that you can generate with the self-service PLECS model generator. This is really useful to include your environment and not use a default model that may not correspond to your environment and may be different and give you wrong or not accurate losses, or not as accurate as if you use your own environment, including the parasitics that affect our losses in our device. We cover also soft switching model, and soft switching we have seen it's useful for LLC, CLLC, dual active bridge, and so on. But also it's useful when you use synchronous rectification to have the value of the losses in the third quadrant. We have a nice loss and thermal plotting data, very simple and very easy to analyze. And you can go very fast because PLECS is a state change simulator, and you can have very fast result, much faster than using SPICE to simulate, as Christian shown before. So now let's go on a very simple example. Here I will take a boost converter, 400 volt in, 800 volt out, 2 kilowatt, 100 kilohertz, using a SiC MOSFET, SiC diode. This is the waveform if I use an ideal inductor here, but no one has an ideal inductor, and the inductor has a parasitic capacitor. Let's take various examples. For example, a 10 picofarad parasitic capacitor on top of my inductor, 100 picofarad and 1 nanofarad. I can see that the peak of current increase depending on this parasitic capacitor. This is the same as increasing the COSS and increasing the reverse recovery. And at the end, what I observe is that the losses in my MOSFET increase with the parasitic capacitor. With the 1 nanofarad, that is a very bad inductor, the losses are mainly dominated by this 1 nanofarad parasitic capacitor in the inductor. And I can capture that with SPICE, and I can capture also the increase of temperature in the MOSFET linked to the fact that I have much more losses due to the capacitor. For your information, this is the bandwidth of the inductor, let's say, or the resonant frequency of the inductor, depending on the parasitic capacitor. You see that having an inductor going to only 160 kilohertz for a 100 kilohertz operation, I'm very close to the resonant frequency, so I'm very close to have a capacitor, and this induces a lot of losses. So now let's do the same example with the Elite Power Simulator. So now it's very simple. I select the boost topology, and then if I want to include the parasitics of the inductor, I will select, instead of using the nominal model, I will select to use a generated model that I have generated, that I will generate with the self-service PLECS model generator. But let's see the result first with the default model. You see here, it's very simple. I have the losses, I have the waveform. PLECS do not take into account the transient, so I have no spike on the current and no spike on the voltage. Now I use the PLECS model generator to generate the PLECS model, And for the load inductor, this is my switching inductor of my boost, I will generate one model per value of parasitic capacitor. So one for the 10 picofarad, one for the 100 picofarad, and one for the 1 nanofarad, and generate those models to use in the PLECS simulator or the Elite Power Simulator to simulate my boost topology. So if I do so with the 3 models here, I can see that my losses increase as we have seen in the previous SPICE simulation, going from total losses between the diode and the MOSFET from 15, 20, and 50 watt. But now let's compare this result with SPICE and PLECS. Do we get the same information with both tools? And this is the result I have obtained with PLECS. This is the result I have obtained with SPICE. And then if I compare for 10 picofarad, I have 12 watt, around 12 watt on both sides. For 100 picofarad, I have 16 watt on both sides. And for the 1 nanofarad, that was the very bad inductor, I have around 47 watt on both sides. So the simulation, when I use a PLECS model, a dedicated PLECS model corresponding to my real environment, I have a good correlation with simulation in SPICE and PLECS. And PLECS is much faster and much helpful, and I can try various configurations to see how the losses will be in my system and what I can do to improve the losses. So this is the end of my presentation, and I will open the stage for the questions.
So thank you very much, Didier, and thank you, Christophe. That was a great presentation. So we have a few minutes for a few questions that came through the webinar. The first one is for you, Christophe. Somebody's asking, why is it important to assess the low frequency ripple in a single phase PFC?
Well, it's always important to look at the RMS current in the capacitor, whether it's in a PFC or in another converter. And that capacitor is going to generate internal losses and heat increase inside the capacitor. And in a PFC, as I explained, the situation is a bit more complex than in another converter because you have 3 components in the, let's say, a single phase application. You have the low frequency components. That's the one I've shown here, which is 100 Hertz or 120 Hertz. It can be quite significant depending on the power level. And then you have the high frequency pulses coming from the converter itself, plus you need to account from the high frequency pulses absorbed by the downstream converter. So the whole, let's say, summation of all these currents make the RMS current that has to be considered for selecting the right output capacitor.
Okay, thank you. And the second question for you, how do you stabilize the DQ loops in a 3-phase PFC?
Well, as I explained, the mathematical treatment for stabilizing the loop it's quite heavy. The solution that I found is to resort to average models. And by using the PWM switch model, as I shown in the slides, I can construct a 3-phase PFC, whether it's 6-pack or Vienna, with SPWM, and I can extract what we call the control to output transfer functions, which is the power stage response using that simulation structure, and apply a compensation strategy to cross over, let's say, 2 kilohertz for the DQ loops and maybe 80, 100 hertz for the voltage loop.
Okay, and we also have a couple of questions for Didier. So somebody's asking how long it takes to generate a custom PLECS model.
This is really quick. I think in 2 minutes, when the server is not busy, you can get the model. Sometimes it can take longer depending on the number of points, but when it takes more than 2 or 3 minutes, you receive an email notification when the model is ready, so you don't have to wait.
The same guy is asking, is the custom PLECS model compatible with PLECS standalone?
Yes, you can use only the PLECS model generator if you have a PLECS license on your computer, and then generate the model and download that model with the library. We provide the file, the XML file, on your PLECS standalone platform. Okay,
I think we have time for last question from last minute question from you, Christophe. What are the typical switching frequency of active PFC? Is there a difference of choice depending on the topology?
I would say it depends more on the technology of the semiconductors. As I said, IGBTs, it's difficult to exceed perhaps 10, 15 kilohertz, depending on the power lever. I've seen very high power converters operating at a few kilohertz. But then as you go to, let's say, higher structures, let's say with higher power levels with SiC or MOSFETs, you can probably push the frequency to 30, 50 kilohertz.
Okay, thank you, Christophe. I think it's noon time right now, so we came to the end of the webinar. All the questions that we were not able to answer, we will be addressed afterwards. So thanks again to Didier and Christophe for the presentation, and thanks to all the attendees to watch the webinar today. Thank you very much.
Merci, Ricardo.
Thanks,
Bye-bye, everyone.
Bye-bye.